Hello, this video is to accompany summarizing historical returns in Excel in many different ways. This is to accompany our discussions in class. I wanted to bring attention to your chapter notes in your Google Drive folder, Business 432, Chapter 5 has Risk and Return in Capital Markets. We had talked about interest rates, what determines interest rates, what they are composed of, and we looked at compounding. Please review the notes on compounding. They are updated on Google Drive. I have added some extra notes about what does this EAR at 656% mean, as opposed to the APR of just 2 times 1.75. I also included some examples that also will be at the end of your book, how to compound returns that are less than a year, but also how to take an average using the same method of returns over a year, okay? This homework that you are going to be working on is to summarize returns of this data set. So this data set is value of $100 invested at the end of 1926. You will be working with return data that can be easily transformed into price data or index price data that you can see here on this line graph. This line graph is one of the ones that I love to talk about. I love showing this to students and everybody who is interested, because seeing the upward trajectory in different asset classes and the slope of that trajectory helps people reduce their degree of risk aversion. We know that the degree of risk aversion is very personal, but we also know from behavioral finance studies that with with knowledge and additional information, people can reduce their degree of risk aversion to be more comfortable in more risky and more profitable investments. This class, summarizing returns and then optimizing your portfolios, is to look at comparing different portfolios, their risk-return profiles, and ultimately choosing portfolios and asset allocations that will fit with your degree of risk aversion. You will put together a table similar to this with a little bit more information. You will calculate average of past returns, the risk premium of those returns, standard deviation or volatility of those returns, maximum, minimum, and a few other statistics that we use to learn more about the distribution of returns that you're working with. This is a histogram of annual returns of common stocks between 1927 and 222. This is the data you're working with. This histogram is exactly the data that you will use for your Excel homework. It shows us here where, this is regardless of time, this is not a time graph, this basically shows us where the annual returns fell. So you just graph the returns 0 to 5, 5 to 10%, and you just look at the frequency of these returns, or in other words, how many of these returns there were. This particular histogram is based on percent of observations. You can also see many histograms that simply have quantities on their y-axis. Either one shows you how many of these returns you had. So about 12% of returns were between 0 and 5%, and then even more, about maybe 13 returns were between 20 to 25%. 13% of observations between 1927 and 2022 fell between 20 and 25%. That is an amazing statistic. 20-25% return, annual return over that period of time can really add up and help you grow your savings. This is frequency distribution of the United States Treasury bills. The Treasury bills is what we use for the risk-free rate. And this is what we use to calculate risk premiums, to learn how much are you getting rewarded for taking on extra risk and extra volatility. The measure of dispersion, standard deviation, can also be observed visually. The more dispersion, or the more bins or categories of annual returns you have, the higher the standard deviation is going to be, and you're going to see it in your data. This is bonds distribution. All of this is available to you on your Google Drive. A few words about normal distribution. Law of large numbers tells us that as our sample size increases, distribution will eventually follow normal distribution. So what is normal distribution? Normal distribution is symmetrical. It can be graphically depicted in a histogram by a bell curve. So typically, generally, your distribution should be a bell curve here. It looks like maybe the distribution of treasury bond returns is closest to the normal distribution. I don't see a specific bell here. Maybe the top here is a little smaller proportionally than what you would see in a bell curve here. But why is this important? Because a lot of statistical functions and formulas and coefficients we use are based on normal distribution. So then if our data does not follow normal distributions, the assumptions or the results from approximations and statistical inferences may simply be biased or not consistent. Therefore, what you will also do in your homework, you will calculate skew and kurtosis of your data. These two are very important in finance. We use them to see whether the data is skewed, meaning not proportionally distributed or not symmetrical down the middle. The positive skew will be one where the peak is actually to the left, but more data is to the right of the zero or mean return. And negative skew was the one where the peak is a little bit to the right, but more observations are to the left. And this is what in finance we are concerned with, right? We don't want more than half of the observations to be negative. So we examine this to see whether it's a problem or not. A skew of 0 is one that you're looking for. If skew is above 0 positive, then your data is positively skewed. If skew is below 0, then your data is negatively skewed. Kurtosis looks at fat tails. Basically, what we're looking at is your data, as opposed to looking at skew, we're looking at the vertical distribution of the bell curve. So a normal distribution here you see will be, it will look like a bell and it will slowly drop off, and then the tails will be small. Data that has negative skew will be fat-tailed, meaning that there will be more observations. There won't be as much of a drop-off as in normal distribution. So there will be more observations to the left than negative observations, and also more observations to the right. Basically meaning that if your data has a negative skew below 0, it will have more extreme observations, to one side and to the other side. If, on the other hand, you have positive kurtosis, then you will have fewer observations here in the middle, and then you will have thin tails, meaning that you have more observations right in the middle, fewer extreme observations. Kurtosis, actually, if you don't subtract the 3, generally we used to think of it as, 3 is the normal kurtosis, but now Excel formula subtracts the 3, and this formula here subtracts the 3. So again, if you have 0 kurtosis, that's good. If it's above 0, it's positive. If it's below 0, it's negative, and it's a risk of having more extreme observations. Last concept that's important in statistics is value at risk. It's a very popular concept by finance practitioners. Hedge funds use it all the time to examine how risky is your portfolio. What does that mean? Well, if you calculate the percentiles of your sample. So if you order all of the observations, all of the historical returns, or the simulated future returns, what will be the 5th worst observation? Meaning, if you look, let's say, 5% value at risk, you are looking at what is my worst loss at 5%, or what's my 5th percentile of the distribution. So you're looking at that downside risk. Now, this is a very, very popular measure. I'll show you guys how to calculate this in Excel. But some practitioners also and theoreticians criticize value at risk that it's just at one point on the distribution line. So we also calculate expected shortfall, which is the average of the 5% worst observations from 0 to 5th percentile. And we can look at value at risk of 10, which would be the 10th percentile of your distribution, and then expected shortfall would be just an average of all of the values below, including the 10th percentile. You will also calculate risk premiums, excess returns, and risk premiums, and we use that to look at the reward to volatility ratio. The Sharpe ratio is the golden standard to compare and rank portfolios. The higher the Sharpe ratio, the better your portfolio is. And what do? Sharpe ratio is simply risk premium of your portfolio. Risk premium of your portfolio divided by the standard deviation of your portfolio. So you calculate the returns and you summarize them, and then you look at what your returns are per unit of risk. This is specifically used for well-diversified portfolio. It's less useful and less appropriate for individual stocks, even though I have seen some people use it as well. It's not exactly correct because we know that there's a lot of idiosyncratic risk in individual stocks that should be diversified away, and in a well-diversified portfolio, that idiosyncratic risk is going to be minimized. Okay, so let's look at your Excel.